Okay, as I was saying, we have a question here. Okay, so I chose to go with RAD because it seems to be much simpler to work with, unlike RAC. So RAD is simply equal to the coordinates of point D minus the coordinates of point A. So in our case, so subtracting point A, which is negative 5 minus 1.5, that which is like negative 6.5. So that gives us the x coordinate, and then the y coordinate. Point D hasn't moved anywhere in the y, so it's 0, minus point A is actually negative 3. So you have 0 minus negative 3 there, which will obviously be positive 3. Then in the Z, both of them, A and D, haven't moved anywhere in the Z. So to just be 0 minus 0 there. So this gives us a vector RAD, which is a 1.5i plus 3j plus 0k. And then for us to be able to resolve the force 80 pounds shown there into its components, we have to multiply 80 pounds multiplied by the unit vector CD, because the direction of the force is actually C to D. So for us to get the unit vector, we need to first get the vector itself, RCD. So the vector RCD is simply the coordinates of point D minus the coordinates of point C. So point D, we're working with it even in the previous thing here, which was RAD. So in the X, as I said earlier on, it's just a negative 5. Then it's also, sorry, in the X it's negative 5. Then you're subtracting point C in the X, it didn't move anywhere, so it's 0. So that gives us the X coordinate. Then the Y coordinate, point D hasn't moved anywhere in the Y, so it's 0, minus point C in the Y, it moved negative 3 added to 4 cosine 45. Because if you look at our door here, it's inclined at 45. So when you take 4, which is the distance of the width of the door, cosine 45 gives us the point C. So when you add the 3 there, we have the total magnitude. Then point D in the Z doesn't move anywhere, so it's 0, minus point C in the Z. It has moved 4 sine of 45. So we have this, we have our RCD, which is equal to negative 5i plus 5.8284j minus 2.8284k. So once we have our vector RCD, to get the unit vector, we are going to simply divide the vector by the magnitude CD. So the magnitude of RCD means the X coordinate, in this case, which is 5 squared, plus the Y coordinate, which is 5.82 squared, plus the Z component, which is just 2.828 squared. By the magnitude 80 gives us the force 80 in terms of its vector component. So in the X, this 80 was negative 48.88. Then in the Y, it was 56.98 there. And then in the Z, it was negative 27.65. So once we have our RAD, And then we have also our force in terms of its vector component. Getting the moment is simply carrying out our matrix here, getting the determinant of this matrix, which I haven't shown here because it's something that I'm sure by now we are all familiar with. But in case there's anyone who has a problem with getting the moment, considering the matrix that you have here, you should be able to ask me at the end of the lecture. I'll explain. So our moment at point A happened to be a negative 2.9i plus 41.5j plus 232k. The units are pounds feet. So on your own, just for the sake of practice, you can even try to get the moment about point B and see the answer that you'd get. Also, I can try, just for the sake of practice, you can try to get the same solution that we have here, moment about point A, now taking your R to be from A to C. And then the answer that you're going to find is supposed to be the same answer that we have here, highlighted in red. So I'm moving to the next question. Okay, so question 4-43. We have a nice diagram here with us, and then we're being asked to get moment about point A. So as usual, getting the moment, the first step, if it's a 3D question like it is in this case, is for us to get it's for us to get the vector, which is going to be RAC in our case. So RAC means the coordinates of point C minus the coordinates of point A. So the x component of C happens to be, that's 0.3 meters plus 0.25, which is 0.55 minus 0, because point A is actually at the origin. So it's 0 there and the x. Then in the y, point C has moved 0.4. Then minus 0 also for point A. And then the z component there, point C is actually negative 0.2 in the z. So minus 0, which is the z component of point A. So we have our vector, which is RAC equal to 0.55i plus 0.4 minus 0.2k. Then the next thing is we have to get our force also in terms of its vector components. So the force 80 Newton there, getting it into its vector components, we're going to multiply 80, the magnitude, multiplied by the unit vector, which is along the line of action of the force 80. So in this case, our unit vector happens to be cosine 30, sine 40, that's in the x, plus cosine 30, and then, cosine 30, sine 40 in the x, plus cosine 30, cos 40 in the y. Then the z is simply negative sine 30, because it's going downwards there. So our force vector happens to be 44.53 I plus 53.07 J minus 40K Newton, because the force is, the unit for the force there is Newton. So our moment will finally be, the determinant of this matrix here, where the first row is actually I, J, and K, which are the unit vectors. Then the second row that we have in this matrix should represent the magnitudes, the coefficients of the I, the J, and the K there, of the RAC. Then the third row there in that matrix gives us the coefficients of the force 3. The coefficient of J was 53.07, coefficient of k was negative 40. So once you get your determinant there, you have your moment about point A, 13.1 J plus 11.4 K. So this is the moment in terms of its vector component. As sometimes you might be asked to find the magnitude of this moment. The vector that is highlighted in red here, to get the magnitude, is the x squared plus the y squared plus the z squared. Then you take the root of that. Then you're going to get your magnitude of the moment A. Okay, so this question was as straightforward as it is here. Then we move to the next question, which is question 4-46. Okay, so this question that we have here is quite an interesting question, in the sense that it's like you are given the answer, which is the moment, and then the vector, which is supposed to be ROP, is actually given, but then I mean you're only given the x component, but then the y you're not given, the z you're not given in terms of its vector component. Then you're taking the moment about point O. Then the question is asking us to get the values of y and z there. This is just similar to a simple scenario that I can tell you. Like, let's say you have 4 plus x. Maybe the answer is equal to 6. So you have the answer, and then you are asked to find, you have the answer in this case, which is the moment. Then now you are simply asked to get the y and the z component of the, that's the first thing that you do here. You get your vector, which is going to be ROP, since you're taking moment about point O. So ROP, you have 1 there, which is shown on the diagram to be in the x, and then in the y is simply going to be, so that its x component is 0, plus z, which is z minus 0, because point O is at the origin, so the z component is also 0. So you have your ROP there, which is like 1i there plus yj plus zk. And then for us to get the moment, as usual, we say moment at A is equal to ROP cross F. Okay, so F is already given in our question there in terms of its vector component, which is very, very good for us because we don't need to resolve anything, which is a 6, 8, 10 there. So once we have your matrix there, moment about point O, in terms of the matrix there, you have y and z there as the only things that you don't know. The moment at O, you have them there, negative 14i plus 8j plus 2k is equal to the matrix there. So once you sort out this algebra here, matrix, you're going to realize after equating the x component of the moment by the x component of the determinant that you're going to get from the matrix here, also equating the y component of the moment, which is 8, to the y component of the determinant you're going to get from the matrix, as well as equating the z component of the moment, which is 2 in this case, equating it to the z component of the determinant of the matrix. You're going to find that your y is going to be 1 and your z is going to be 3. So that's how you're going, that's how you get your y and your z there. And then the question asked us to further get the distance d. So remember, moment is simply force times distance in another language, like in the scalar language. Moment is simply the distance times the force. So in this case, if you're looking at that formula, moment is equal to Fd, where the force, the moment there is the magnitude, and the F there is the magnitude of the force. And then D is a perpendicular distance from the point of, from the point where the moment is being taken from up to the point perpendicular to the line of action of the force. Okay, so on our diagram there we have point D shown. So the only thing here that you're supposed to do is to get the moment, to get the magnitude of the moment and the magnitude of the force. Then you use the formula there, which is M is equal to Ft. So getting the magnitude of the moment, I haven't shown it here, but the answer is 16.25. If you need the formula for magnitude of a moment, it's simply the square root of the x component squared plus the y component squared plus the z component squared. So in this case, the magnitude of the moment was simply the square root of 14 squared plus 8 squared plus 2 squared. So you have 16.25. The same thing you do also for the force. The components of the force were given in the question to be 6, 8, and 10. So the magnitude was the root of 6 squared plus 8 squared plus 10 squared. The magnitude of the force happened to be 14.14. So once you plug them in that equation there and the formula here, which is M is equal to Ft, you have your D to 1.15 highlighted in red there. So it's a very nice question. I'm sure it's quite clear. Then I'm moving to the next question here, which is 4-48. So question 4-48 has some nice principles. We have a diagram that we have here. And then the question asked us to get the moment of the force 400 Newton about point A. So the tricky thing about this question is, for us to be able to get the moment, as usual, we have to have our force in terms of its vector component if you're dealing with 3D. So the 400 there that you are given is just given as a magnitude 400. But how do we get its vector components? So we know we're supposed to multiply the magnitude of the force 400 by the unit vector, which acts along the line of action of the force. So in this case, our unit vector that our unit vector is going to be okay. Let me explain this first. The line of action of the force there shows us that it's actually perpendicular to the line AC, and it's also perpendicular to the line BC. And there's a principle that says if you have two lines and then you want to get if you have two lines that are meeting at the same point, in this case point C, and then you want to get a third line which is perpendicular to both of the lines. So in this case, we want to get a line that's perpendicular to the line AC as well as the line BC. So to get that, we'll simply get the cross product of AC crossing it to BC. So when you get the cross product of the two lines, the result of that will be a vector which will act in the direction of the force 400. So this thing I've explained In case I'm not so clear and my explanation is highlighted in red here. Once you have the slides, so once you have the slides, you should be able to go through and get the understanding in case you haven't understood what I mean. But yeah, it's highlighted here in red. AC to BC. So the first thing I get the vector RAC. So in the X, point C is actually 0. Then also in the X, so in RAC, yeah, so point C in the X, yeah, in the X is 0. Point A also in the X is 0, yeah. So it's minus 0, that's 0i. Then in the Y, point C is actually 4 meters away from the origin in the Y. So it's 4 minus point A is actually 0 in the Y. So it's 4 minus 0 there. Then point C in the Z is actually 0 because it's on the base there. Then point A in the Z is actually positive 3. So it's 0 minus 3. So this gets us the vector 0i plus 4j plus, minus 3k. Then you also get another vector which is RBC. So the coordinates of point C minus the coordinates of point B. We can see there in the X is 0, point C, then minus 3. That's the magnitude of point B in the X. Then put 4 minus 0 there. Then you got 0 minus 0 because point B and point C are actually at the base there. So their Z is just 0, 0. Then you have your vector there. Then crossing the two vectors here, you're going to use the same thing that's used to get moments, which is the matrix way of going about it. So when you get the determinant, you find that the result plus 12k. So 9j plus 12k divided by the magnitude of the magnitude, which is the root of 12 squared plus 9 squared plus the unit vector there. So multiplying the unit vector by the 400 vector component, and it happens to be 249.88 I plus 187.4 1j plus 249.88 k. So that's the force in terms of its vector components. And then for us to get a moment about point A, as usual, we will have our R, which will be defined as RAC. So RAC, we already got it there. So we can see it's 0i plus 4j minus 3k. So crossing it with a crossing it with the vector component of the force 400. That is shown in the matrix there. When you get the determinant, you find that at the moment will be 1.56i minus 0.750j minus 1k units kilonewton meter. The only tricky part was to resolve the 400, meaning you needed a vector that was perpendicular to both lines AC and BC, and that is gotten by just simply doing the cross product of the two lines there. So hope it's clear. I'm moving to the last question for this session, which is question 4-50. So this is also an interesting question because it helps you this question helps you to just exercise your skills on how you resolve your forces into their vector components given the angles. So I've got a disk there which is pinned at point O, and then you've got point B there, and then you've got point A there. Then the force, which is equal to 450 Newton, is actually in the direction A, B. And then the question is asking us to get the moment about point O. So for us to be able to get the moment about point, the first thing is we have to get our vector. In this case, it can either be R or A, or whichever one that you are comfortable with. And then the force should also be in terms of its vector component. So getting the force 450 in terms of its vector component, you have to first get the unit vector from point A to point B. So that was that's just like the tricky part about this question. So getting the unit vector from point A to point B, you first need to get the vector from point A to point B, which is simply the coordinates of point B minus the coordinates of point A. Then you divide by the magnitude. Okay, so in this case, point B in the X is actually 0. So point B didn't move anywhere in the X because B is actually above, right above the y-axis there. That's where point B is. So it didn't move anywhere in the x-axis. So it's 0 there minus the x component of point A happens to be the x component just happens to be 0.5 there, which is the radius, sine the angle 30 degrees there. The 30 degrees I'm talking about is this 30 degrees in the horizontal, not the vertical 30 degrees, but the horizontal 30 degrees. Yeah, so it's 0.5, which is the radius from the center of the circle there, point A, 0.5. When you say sine 30 degrees there, you have the x component. So the difference there gets us the x component of A to B. Then the y component, look at point B there. In the y, you have in the y, point B moved 1 cosine 30. This one is the magnitude from point O to point B, because the radius of this circle is 0.5. So 0.5 plus 0.5 gets us the magnitude from point A, from point O to point B, which happens to be 1. So when you say 1 cosine 30, the 30 degrees I'm talking about here in this case is this 30 degrees vertical. I mean vertically upwards to point B. So you get, when you take use of the cosine, you have your x, I mean your y coordinate of point B there, minus the y for point A happens to be 0.5 plus the 0.5 sine 30 is the one that's shown in because this diagram, there's that part which is in green, then the other one is in brown there. So the bottom part there, which is in brown, that's where the 0.5 is coming from. Sine the angle there, which is 30 at the bottom there. So that cosine 30, that gets us the y coordinate of point A. So you get the difference, you have your y component of the vector A, B. In the same way we get the z component of point B, which happens to be simply 1, which is the distance from point O to point B. Sine here is the 30 degrees, which is vertical here. So minus point A is actually at the base there, we can see, so it's 0. It doesn't move anywhere in the Z. So when we do this, we'll be able to, I mean, when we divide this vector by the magnitude, we're able to have the unit vector. So to resolve a force in terms of its vector components, as usual, we always multiply the unit vector by the magnitude of the force. So the force happens to be negative 199.82 minus 53, and then we should be able to have a discussion before this group ends. I mean, before this meeting ends.
You know, it seems to have a challenge with our
network. Me unmute you. Network?
We challenge with our network. Anyone with a question? Those who have got questions.
Yeah, we've got some people here with questions who've raised up their hands.
Oh, okay,
so
okay.
All of us
we
with
can
questions.
Just give them a break for 2 minutes. Those who have got questions, please be ready. Okay.